Okay, in this lecture, we'll study about beams, and then later we'll see the expression for a bending moment inside the beam, right? So here you can see the figure. So I have drawn a beam over here, and we have shown the cross section of the beam as well. So it can be supported at its end with different kinds of support. So the left support, usually you can see here, it is a fixed support, and right hand support, you can see here the rollers. So it is called as roller supports. So let's not worry about the kind of supports we use in a beam itself. So for the simplicity, we have assumed this particular beam with a cross section of a rectangular shape. So again, we assume that this cross section remains uniform throughout the length of the beam. And again, it can be any kind of shape, but for the sake of convenience, we have assumed it to be rectangular. Now this beam is subjected to some kind of vertical load. So this load need not be vertical all the time. It can be acted in any direction, and it can not necessarily be point load itself. So you can have a distributed load over the span of this beam. So again, let's not go into the details of the loading and details in the cross section and all. So let us consider a simple beam which is being acted upon by a vertical point load as shown in this figure. So by the intuition, when we load this particular beam with vertically downward load, point load, this beam can assume this particular shape as shown in this figure at the bottom, right? So now what we need to study here, so this, look at this beam again. So this beam, you can consider this as a top layer of the beam. This can be as a bottom layer of the beam. And as this is a continuous body, what we call it as a continuum body. So you can assume that this continuum body or beam is comprised of different sets of fibers. So I have shown such three fibers along the length of the beam here. But remember that it is not a finite number of fibers because this is a continuum body. So in between also we have many fibers in this particular beam. So you can say in brief that this beam is comprised of such infinite number of fibers. Okay, so all right. So we have infinite number of fibers in this particular beam over here as shown in figure. So if you look at the top surface here, so if you look at the top surface of the beam here, when it is acted upon by vertically downward force, this point is stretched inwards. So this is by intuition. Look at this. So this was your point load over here in this vertical direction. So that's why this top layer at the end points of this top layer are stretched inwards. At the same time, if you look at the bottom layer, so the points on the bottom layer are stretched outwards. So from this intuition, we can say that this top layer of this beam is under compression, because this is tending to decrease the length of the top layer, right? And as these points on the bottom layer are stretched outwards, so bottom layer of this beam, you can consider it is under tension. So it is stretched outwards, that's why it is tending to increase the length of this bottom layer. So that's why we can call this as the top layer is under compression and the bottom layer of the beam is under tension. So again, if you look at the fibers in the middle, so between top layer and bottom layer, so I have drawn again three such fibers over here. So look at these three fibers over here. So again, by logic, if you see, the top layer is under compression and bottom layer is under tension. That's why if you go from the top to bottom, there are certain fibers which are under compression, and as you keep moving downward, you'll find certain kind of fiber which is not under compression and not under tension. So this length of this fiber, so this compression means this length of this fiber is going to be decreasing, and under tension, the bottom fiber, this length will increase. So if you go if you go from top to bottom layer, there has to be certain fiber for which the length should remain constant. For which the length will remain constant. So the top layer under compression, bottom layer tension. So as you are going from compression to tension, there has to be certain layer or certain fiber which is neither in compression nor in tension. So what it means actually, its length is going to be constant. Its length is going to remain constant. It is not going to stretch or compress at all. So such fiber is called as a neutral fiber. Such fiber is called neutral fiber, or the line along which this fiber occurs is generally known as neutral axis. So this is called as neutral axis. So again, suppose if you consider this cross section here, so you had this particular three sets of fibers. By this kind of loading, you have this particular top surface is under compression, this bottom surface, this is under tension, and as you keep moving downward in this through this cross section of this beam, so there has to be certain fiber which is not under compression and tension. So this fiber is called neutral fiber, or the line along which this neutral fiber is present is called as neutral axis, generally represented by Na, neutral axis. And again, if you go through the cross section of the beam, this is actually in fact a three-dimensional body. So you can consider this beam as this particular three-dimensional object. So let me draw this particular three-dimensional object. So let us see, this is the how this is our beam. Okay, so this top surface, this top layer is under compression because we have loaded this particular beam with a point load in vertically downward direction. This bottom layer is under tension, and if you see here, let me draw this particular diagram completely. So this was your original shape of the beam, and if you see a layer in between somewhere, not necessarily at the middle of the beam, okay, so that is another story. So we are not going to discuss that here right now. We'll discuss in the further lectures. But if you look at the layer in between top layer and bottom layer, somewhere in the middle, not exactly at the middle. So this layer, this is neither under compression nor under tension. So this layer can be called as neutral layer. This layer can be called as neutral layer. So in fact, for three-dimensional object, it is a kind of surface. So you can call this as a neutral surface as well, or neutral layer as well. And if you consider only two-dimensional object as shown in this figure and assume that nothing is going to happen in third direction, let's say third direction is Z direction. So you can say that this particular length is called, this can be termed as neutral axis, or the line along which this happens, the line or the fiber which is neither under compression nor under tension, this can be treated as neutral axis. So this is the definition of the neutral axis. So neutral axis. So if you consider this particular, suppose, let me call this as first fiber as A, B. Let me call this as a P, Q, and let me call this middle fiber as C, D. Now, once we apply this vertical load, so this will become A dash, B dash. Let me call this as a C dash, D dash, and this third fiber would be P dash, Q dash. Okay, all right. So now if you look at the fiber AB, so AB has become A dash, B dash, and this is under compression. This is under compression. If you look at the fiber PQ, it has become P dash, Q dash, and this fiber was under tension. And if you look at the fiber CD, which is along the neutral axis, it has become C dash D dash, and it is neither compression, no compression, and no tension. So this is neither under tension. So it's the length of this fiber will remain constant. So this CD and C dash D dash, these lengths are actually constant. Now, if you look at the other fibers AB, AB is under compression. So this, due to compression, this A dash B dash will be smaller. So this AB will be larger than A dash B dash. That's what the length of this AB fiber because of compression has now reduced. And if you look at the PQ fiber, the PQ fiber is under tension because it is below the neutral axis. So all fibers below the neutral axis are under now tension, and all fibers above the neutral axis are under compression. And neutral axis is not under compression and not under tension. So its length will remain constant. For the fibers under compression, length is going to reduce, and for the fibers under tension, length is going to increase. So for this PQ, now this length has increased and become P dash Q dash. So this is what happens when you load a particular beam. So we have in each and every beam whenever it is loaded with certain kind of load, there has to be certain neutral axis. The fibers above neutral axis are under compression or tension. I'm saying under compression or tension because it depends on the load. Suppose if you would have applied this particular load in opposite direction, then this bottom fiber would have been under compression and top fiber would have been under tension. But that depends. But remember, on either sides of neutral axis, you have either compression or tension. Suppose top on the top surface or the for the fibers above neutral axis, if those fibers are under compression, then the bottom fibers or the fibers below neutral axis will be under tension and vice versa. But neutral axis will not under is not under tension and is not under compression as well. So its length is going to remain constant. So this is called as neutral axis. If you consider 3D, it is a kind of surface. So it is termed as neutral surface also. Now, let us discuss how to find the bending moment. How to find the bending moment in a beam. So again, I have drawn a deformed shape. So this is changed. Suppose you have applied a load on this particular beam and now this beam has assumed this particular shape over here. So you can see here, there is a neutral axis as shown in this particular figure. This top surface, as the length of this particular top fiber has now increased, it is under tension. And if you see at the length, for the length of the bottom surface, it has reduced, so it is under compression. Okay, now let us assume that this particular shape of the fiber is a kind of arc. Okay, so this bottom fiber is an arc, the top fiber is an arc, so the neutral axis is an arc, and these arcs are of concentric circles, so they have a common center which is located at O, this point O. Now I have marked the radius capital R of the fiber corresponding to this particular neutral axis. Okay, so this is called as the radius of curvature of this beam. So this, let me write this as radius of curvature. This is radius of curvature of beam, because now beam is now curved and we have assumed that it is kind of a circular shape basically. So it is a part of circle. That's why we have called this an arc, and the radius of this particular arc corresponding to neutral axis is denoted by capital R. So radius of curvature of this particular beam over here. Now again, I have assumed one more layer or one more fiber above the neutral axis at a distance y from it. So this y is a distance of fiber, distance of any fiber for that matter, fiber from neutral axis. It is from neutral axis. It is measured from neutral axis. Now we have to see the relation for the bending moment, how to find the bending moment. Okay, so let us see what happens here. So if you look at this particular fiber, let me write this as now A dash and B dash. Now let me find the length of this fiber AB. So fiber AB, we have considered fiber AB. Barabar? Okay, fiber AB before load and after load. We'll find its length before load and after load. Now after load has applied, now its length has become A dash B dash. Now as we have assumed this shape to be a part of circle, so length of arc can be given by, so suppose this angle, let me define as theta. Let me define this angle as theta. So length of arc is given by r times theta, radius times theta, but the distance, this radius for this A dash B dash fiber is now r. So this is basically r plus y times theta, plus y times theta. And before load, the length of fiber. So before load, if you see here, oh sorry for this. So this is a beam. This was your neutral axis and this was your original AB at a distance y apart from neutral fiber. So now if you look at the length of neutral axis, so length of neutral axis in deformed shape, it is r radius times theta. It is r times theta, right? So, and we have seen that the length of the neutral axis is not going to change. And if you look at the configuration of the beam before loading is being applied on it, all fibers have same length. So before load is being applied, so length of fibers, all fibers are same. And now again, this neutral axis, it has not changed its length. That's why this original length of this AB fiber would be r times theta. So change in length. So change in length for fiber AB. If you look at the change in length for fiber AB, let us denote by delta L. This would be change in length would be final length r plus y times theta minus original length r times theta. So it would be y times theta. And as it has changed its length now, let us find the strain in this particular fiber. So strain is defined as delta L, change in length over original length. So change in length we have obtained as y times theta, and its original length being before load is being applied, that is equals to r times theta. So this would be y times r. This would be y times r. So we have obtained that the strain, this is the strain is equals to y divided by r. So we have obtained one important relation, that if you look at the fiber, so this y is the distance of any fiber from neutral axis. Now suppose if you consider the neutral axis itself, so the distance of neutral axis from neutral axis would be 0. So in that case, y would be 0 and your strain would be 0. That is what we expected, because we have considered that this neutral axis is such fiber which is neither under tension nor under compression. So its length of this neutral axis is not going to change. So for the neutral axis, strain would be 0. Now we have obtained the relation for the strain of a fiber which is located at a distance y from the neutral axis, and it is given by y divided by r. So now let us look at the bottom figure here. So I have shown this particular cross section of the beam over here. So suppose this is a particular cross section of the beam over here as shown in this figure. So again, this dotted line is a neutral axis. Okay. So you are looking at the beam from the side view, and you have considered this particular fiber, this particular small cross section, which is at a distance of y from it. And now as this top surface, this top surface is under tension, this bottom is under compression. So this particular cross section, small cross section, is also under tension. And as it is under tension, certain force has to be applied on it, or certain force has to get applied on it. And this is represented by some sort of stress. So this sigma is called as bending stress. This sigma is called as bending stress. Now, because look at this fiber, because this top surface is under tension. Tension means there has to be certain force. Compression, again, there has to be certain force. And it is being acted upon on certain kind of area. Let's denote this small area by dA now. So the force, net force acting on this particular cross section would be stress times area, because our stress is defined as force per unit area. So I am denoting this force as a stress sigma times small area dA. Now this force is being applied on it. All right. So now we have the relation between stress and strain. What is that relation? So stress, so this is the relation, stress over strain. So stress over strain is Young's modulus. Young's modulus. So that's what we write this in a notation here. So stress sigma divided by strain is given by y divided by r. And let us denote this Young's modulus by letter E. Generally, we represent by capital Y. So to avoid the repetition of this variable y and to avoid the confusions here onwards, let us denote the Young's modulus by capital E. So what we have got here, so this sigma over E is basically y over r. Now we have got one more relation. This relates what terms here? Look at these terms. This is stress. This is Young's modulus. Y. is the distance of fiber from neutral axis, and r is the radius of curvature of the beam. Okay, all right. Now, till this point, we have not introduced any kind of bending moment so far. Now, from here onwards, we'll introduce the bending moment. Again, refer this particular diagram here. Now, if you see any fiber below this neutral axis, so the bottom fiber is under compression, top fiber is under tension. So on this cross section above neutral axis, the force is applied as a tensile force, and it will try to stretch this particular cross section outward. So as shown by this particular arrow mark here. And if you look at the fiber below this neutral axis, so this is under compressive loading. So if you look at the force being acting on this particular fiber below the neutral axis, it would be kind of compressive load, and it will try to compress that particular fiber towards left or towards inside. So these two forces, being tensile and compressive in nature, are in opposite direction, and they are separated by certain distance. And you know, when two forces are opposite in direction and separated by certain distance, they are going to produce certain kind of moment, and this moment is called as bending moment. So bending moment is the reason. So the reason for the bending moment is certain fibers inside the beam, let's say the fibers above the neutral axis, are under tensile force, and the fibers below the neutral axis are under compressive force, compressive loading. So that's why, due to this opposite direction of these forces separated by certain finite distance, it is going to produce a moment, and this moment is called as a bending moment. So we are going to find the bending moment applied due to this particular tensile load over here. So let me erase this particular diagram and let me write only for the bending moment now. So again, now we have obtained the relation that, let me write basic relations. What we have obtained: strain is y divided by r, and by stress strain ratio, stress is given by sigma divided by strain y upon r, that is equal to Young's modulus denoted by E. So from that we have obtained sigma over E is equals to y divided by r. Okay, all right. Now again, let me draw that particular cross section of the beam over here. So this was the cross section of the beam. So this was kind of neutral axis, and we have considered certain fiber which is under tension at a distance. This distance is y from the neutral axis, and this cross section we have denoted by dA. Now as this is under tensile force, let me draw this force acting on it is given by stress times small area dA. Now to find the moment, let me denote bending moment by letter M. Bending moment. Bending moment is, let me denote by letter M. I have to find this as. Now, what is bending moment? So bending moment is force multiplied by distance, and we are finding about neutral axis. We are going to find this bending moment about neutral axis. So this force acting is given by sigma times dA, and it is at a distance of y from the neutral axis. So this is basically a neutral axis. So the small bending moment, let me denote this as a dm, is equals to force. This is force multiplied by distance. So what is this distance? The distance between neutral axis and force. So this is what? This is sigma times dA multiplied by distance of separation of that particular fiber from neutral axis is y. So if you look at this formula, so here from here you can write this as, so this dm would be sigma. Sigma from this would be given as ye divided by r multiplied by y times dA. So I can simplify this as E over r times y square dA. So this is due to this particular fiber, this particular small cross section. You would have another fiber over here, it will have another cross section. So you have to consider bending moments from all of this. So basically you have to sum all these bending moments due to all set of fibers on this particular cross section as shown in this particular figure over here, right? So either you can do it as a summation, or as this is a continuum body, we have to integrate. So summation is only for the discrete variables, but our variable is continuous, so we'll integrate. So this bending moment is basically integration of m over this particular area. This is the area of cross section. This area is area of cross section. This is called as areal integration. So integration over area. So if you integrate this particular thing over here, this is E upon R. This is y square dA. Y square dA integrated over area. So E modulus of Young's modulus. So you can take it out. It is constant. R, your radius of curvature, is constant. So it is integration of y square dA over area. And if you look at this particular term over here, so what is y square times area? So integration of y square times dA integrated over area can be considered as summation of y square times AI. Summation of y square times dA, small areas. So I, integration over I. So what is this? This is equal to moment of inertia. This is equal to moment of inertia. So moment of inertia, you would have learned this in your 12th standard, right? So moment of inertia of a block. So you know you how you find. So this is geometric moment of inertia. You would have learned something different. Mass moment of inertia. This is geometric moment of inertia. So how to find it? You have to square the distance of that particular cross section from certain fixed reference. So let me draw the diagram over here. So let me write, this is the cross section of the beam. Now you have considered this particular area of cross section. You have denoted this by dA. It is at a distance of y from the neutral axis, and you are finding moment of inertia of this area of cross section about neutral axis. So how to find it? So consider area dA, distance y, square the distance and multiplied with area. So it is y square dA. So this is a particular small area. You have to do it for all fibers. So sum it up. So it will be summation of y square dA. So this term is basically, this is E upon R and multiplied by, this is moment of inertia, generally known as geometric moment of inertia or second moment of inertia, because we square the distance. All right. So let me denote this as I. So what we have got here, therefore, this bending moment is given by EI divided by R. So let us understand the terms here. M, bending moment produced in beam. E, Young's modulus of this beam material. I, geometric moment of inertia. And R is the radius of curvature. And now in this formula, this EI term is termed as flexural rigidity. Flexural rigidity. So what is flexural rigidity? Suppose in case if your R is unity, so bending moment is radius of curvature is unity. In that case, your M is equal to EI. So how you define your flexural rigidity? Flexural rigidity is the bending moment which produce unit radius of curvature of cross section of the beam. So it is that value of bending moment M which can produce the unit value of radius of curvature. So this is how we define flexural rigidity. So flexural rigidity is actually the multiplication of Young's modulus of material of beam and the geometric moment of inertia of cross section of beam. So this quantity depends on E. E means it depends on the material of beam, as well as it depends on the cross section, means how the cross section looks. So whether it is circular, whether it is rectangular, whether it is square, or there are certain different cross sections like I section, T section and all. So basically this flexural rigidity depends on both the beam material and the shape of cross section of the beam itself. So finally, what we have got over here is, so if you look at this particular, you have E over R here. So let me modify this expression as sigma over Y is equals to E over R. And from this expression, you can write this as E over I can be written as M over I. So you have got this relation here. Sigma over Y is equals to E over R. And from this relation, E over R is equal to M upon I. So this is what we got for any kind of beam. Sigma bending stress, Y is the distance of that fiber from neutral axis, E Young's modulus, R radius of curvature, M bending moment, and I geometric moment of inertia of cross section of beam. And again, if you write the expression for sigma itself, it would be my divided by I. So this is a famous expression which we later use to find, this is a bending stress, which will use to find the bending stress when we know the bending moment being applied on the particular beam. This is Y is the distance of that fiber from the neutral axis, and I is the second moment of inertia of cross section of the beam. So this is a famous expression we'll use in further topics like strength of material, solid mechanics, if you are going to learn all these things. And when you find this bending moment diagrams in applied mechanics, shear force diagram in applied mechanics, then you'll often use this particular relation. So you can note this down, particular relation, and this is the final relation what we have obtained. And so again, I'll repeat the terms over here. The sigma is the bending moment, Y is the distance of fiber from neutral axis, E is Young's modulus, this capital R is the radius of curvature, capital M bending moment, and capital I second moment of inertia. So in the next lecture, we'll discuss how to find this second moment of inertia in brief only for the rectangular cross section, and we'll see how the beam gets deflected when the load is applied and how to find that particular deflection.